Hello, everyone, and welcome. Today, we're going to discuss behavior targeting at scale, or in other words, how did we know this ad was relevant for you? I'm Chandra, and with Savin, we'll present a little bit about what Rocket Fuel does, go on into behavior targeting, and then move on to challenges about it. At a 50,000 feet view, Rocket Fuel essentially connects advertisers on one side and the billions of consumers on the other side. And the way we do it is that we integrate with real-time ad exchanges, which enable us to deliver millions of impressions to users on all their devices. And this is a continuously learning process. So we learn from what we deliver, we measure, and we continuously improve. If you move down a little bit, zoom in a little bit, and come down to a 40,000 feet view, you can think of the display advertising ecosystem as kind of having two sides. On the one side, you have publishers such as New York Times, CNN, and so on. And on the other side, you have advertisers and ad agencies. Typically, the publishers integrate with ad exchanges. The best way to think of an ad exchange is something similar to like a stock exchange, except the commodity being traded here, instead of being stocks, is ad placement opportunities. And exchanges are typically run by large companies like Google, Yahoo, and so on. Rocket Fuel integrates with these exchanges and with other data partners to run the advertisers' ad campaigns on their network. So essentially, we can place ads on any of these publishing websites, and we can do it in real time. And there is a continuous optimization going on where we are able to measure what we serve and continuously optimize from it. Now, if you dig a little deeper into exactly how this programmatic buying works, let's say you as a user, you're at a web browser, you're about to go to a content web page, such as Huffington Post or CNET. Your browser is going to send a page request to that web server requesting that content to be loaded. Behind the scenes, the publisher web server is going to make a call to an ad exchange, essentially saying that, OK, here is user number 1234 on my website. Do you have any ad to show for this? And the exchange would make a bid request out to all the technology partners who are integrated with that exchange. So in our case, there is a bid request that comes into the Rocket Fuel's ad servers. Our ad servers consult our campaign data, user data, and figure out what is the best ad to serve. So for example, the user data here includes all the user interactions that we maintain, as well as augmented user information that we might get from other data sources. Using attributes of this campaign and user and so on, our predictive models essentially come up with a propensity score. This is essentially a score that predicts how likely this ad will be relevant for this user. Once we find such an ad, we decide the price to bid for this, and we respond to the exchange with this bidding price. Internally now, at this point, the exchange is going to conduct an auction. The bid request was sent to all the technology providers that have integrated with that exchange, and each of them could have submitted a bid. The auction will happen inside the exchange, and if Rocket Fuel had the highest price, its ad would be chosen as the winning ad. This ad now gets rendered on the user's browser in real time, and the user, along with the rest of the content, also sees the ad on their browser. Now, let's say the user engages with the ad. It could be either they click on the ad, or maybe they see the ad today, and then they visit the advertiser website tomorrow. In each case, we get a notification about the user engagement, and we record that user engagement in our user store. Now, this ad impression and this engagement now serves to refine our predictive models. Our models can now learn, OK, what are the attributes of this interaction that resulted in this engagement? And they can make a better prediction the next time there is a bid request. Going a little deeper into real-time auctions, you can think of a bid interaction as having many different attributes. For example, there are a set of attributes about the user. They could be already known to have certain brand affinity. What time of day is it? what part of the world is the request coming from, are they at a news website, or are they at a sports website, and so on. We use all this information to score the set of eligible ads in our system to identify which ad is the most relevant one. To go a little deeper in this, let's say there are 3 candidate ads. There is ad number 1, which is an ad for lead generation and for increasing sales. There's another ad that is geared towards increasing coupon downloads. And let's say there's also a third ad, which is used for improving brand awareness. Now, for each of these ads, we'll essentially calculate an impression scorecard. You can think of this as essentially take each of the attributes of this interaction. What kind of demographics does the user belong to? What kind of brand affinity they have? And then score it using the weightages that our models provide. And you can imagine each of these ads essentially ends up with a scorecard. And we pick the one that we think has the highest probability of a relevant interaction. The models themselves take in many thousands of features, and they try to achieve a balance between fitting it perfectly for past data versus making a general prediction for future events. And every interaction that we learn about the user is used to refine the models. The models themselves are cross-tested against each other so that we always know against real traffic which models perform the best. Now, to give an idea of some of the scale that Rocket Fuel operates in, typically on a given day, the number of searches on Google is about 6 billion, give or take, while the number of events that Rocket Fuel processes in a given day is closer to 50 billion. So you can imagine the specific challenges that come with it. And this system is made possible by having more than 2,000 servers with about 200 terabytes of main memory and close to 40 petabytes of storage. And the growth has been pretty phenomenal. For example, just to give a snapshot over the last 1 year, our data warehouse increased almost 8 times, including even in the number of servers and in storage capacity. So now we have an idea of the overall ecosystem that Rocket Fuel operates in and an idea of its scale. We'll move on to exactly what we mean by behavioral targeting and the challenges that come with it. At a very high level, behavioral targeting is leveraging a user's online activities to learn about their long-term interests and short-term interests. An example of a long-term interest is if the user is going to be interested in a luxury car or not. An example of a short-term interest is if the user is looking for a pizza right now. And the goal is to expand the user set beyond just simple retargeting. It's not just enough to say that I know a user visited this website and I'm going to continuously chase after them and target them, but it's also to identify new users who may not have been targeted earlier at all. And the behavioral targeting system at Rocket Fuel relies heavily on Hadoop and HBase. On the left, you see all of our ad-serving data centers. Every impression they serve and every event with the user, they record it in logs. And the logs are brought into the Hadoop system. We run MapReduce on them, and we extract relevant behavioral targeting features and store them in HBase. Now, when we train a model, we essentially take the log data, we label them based on whether was this a successful interaction or did this ad not lead to any interaction. We train the model, we test it against past data to make sure the model is of good quality. We calibrate it against real-world data to make sure it is an accurate prediction, and finally come up with a prediction model. We take all the features we have in our HBase system, we use the model to refine it. We figure out which features are deemed relevant by the model and which ones are not, and we only take those features that are deemed relevant, and we generate a behavioral profile for that user. This profile itself is then uploaded to our serving data centers, which can use them for future predictions. To just give a flavor of where the pipeline runs in, it runs on about 650 slaves. This is shared with other jobs, of course, and close to 20 petabytes of storage. And the MapReduce slots in this cluster are co-located to run HBase so that we can run offline processing efficiently. Now let's walk through a specific user interaction and see how these features are generated. Let's say a user visits a BMW website at a certain time. A few minutes later, they go to another website, Pizza Hut. And a minute later, they're back at another car website, Honda. So you can imagine us taking a time window, let's say 30 minutes, looking at all the visits they did in that time, and coming up with a list of here are the sites they visited, and here are the categories they visited. So in this case, the category cars would appear twice in that window, while each website would appear once. Now, the events for the last n days are then read to form our behavioral targeting profile. So the profile itself includes the site, the most recent timestamp the user visited that site, and the activities of that user in the earlier time. For example, how many interactions did they have over the most recent 6 hours, how many did they have in the prior 6 hours, and so on. So this is calculated for each site and each category. And finally, this profile is used to figure out the relevant features. For example, recency. What was the most recent time the user visited this category of website? The frequency, how often did they visit a car website, and so on. Then the model that we use in HBase itself relies on a single column family. So you can think of a column family, let's call it U. And the access itself is done by a row key, which is based on anonymized user ID. And the column qualifiers themselves, they embed the date, the hour, and the type. In this case, whether it was like a website or whether it was a category, and so on. And the cell values themselves are protocol buffers, and they record the most recent timestamp and all the event details relative to that timestamp. And what this kind of organization allows us to do is to access records for a given user very efficiently. Because the rows are keyed by user ID, we can access it very efficiently and get all the events for a certain user. Not only that, we can also access a range of events by using the date and the hour. Because most of the interactions that we care about are what did the user do in the most recent n hours. And these kind of interactions are very easy to do. We can just use a column qualifier range to do that. So with that introduction of behavioral targeting and how we use HBase, I'll turn it over to Savin to talk about the challenges associated with running behavioral targeting at this kind of scale.
Thanks, Chandra. Hey, guys. So before we move on to challenges, I would just like to share a small anecdote. So like a couple of months ago, I and Chandra, we were just sitting around, we were evaluating what kind of inferences our model was spitting. And we found that for a cruise liner campaign that we were running at that point of time, the most important prospects were students who were visiting career websites, right? Like, it seems pretty different, like, why would students care about cruise liners? But 2 months ago, it was like graduation season, students were graduating, and they were interested in probably a grad trip, right? So that's the power of behavioral targeting that it brings to our campaigns. Now, when we have insights these strong, we would definitely have very strong challenges that we need to overcome. So we'll run through quickly through some of the challenges that we have faced, some of the solutions that we came up with, and we hope that you would find something useful out of this. So specifically, we would like to focus on 3 of the challenges. User profile freshness, so we'll talk about why latency of user profile is important and some solutions around that. We have scaled pretty fast, if you have read about us, so we'll talk about that as well. And we would talk about generic scenarios when your pipeline fails, you have mission-critical pipelines, and quick recovery is very important. So let's start with user profile freshness. So our internal research shows that recent activity for any user is a very good predictor of user behavior, and it's pretty apparent as well, right? So let's say you are probably hungry and you are looking for a pizza. So from intent to conversion, the whole time period is going to be probably, what, from 10 minutes to not more than a couple of hours. So it's really important for us to figure out that information propagates to our ad server. Then we need to curate that information, push it through our behavioral targeting pipeline, and make it available to our ad servers for bidding. So latency is pretty crucial. And we, in our research, have seen pretty amazing results when we minimize the latency as far as possible. So we'll talk about a couple of solutions around that. So So one of the solution is pretty straightforward, and I assume that you would be also implementing that. So as Chandra mentioned, we get logs on our ad servers, and they are pushed to HDFS by a process known as scribe. And then our behavioral targeting pipeline overtakes it, so it extracts the features, scores them, filters out a user profile, and uploads it to our online stores. But what we decided to do when we saw that latency was so important, we decided to break that source data into multiple chunks. So instead of processing at the end of the day or at the end of every 12 hours, we process much faster, but though often at the cost of resources. So as soon as a small specific chunk is available, we push it through the whole pipeline. So what we achieve by doing this is that our end-to-end latencies are reduced, but of course we oftentimes end up using more resources. So this is probably an example of horizontal scaling. If you have more resources at your hand, then you should probably go by this route. And that has been very efficient for us. And we'll also talk about this later as well, when this would come in handy about monitoring and fast recoveries. So the next thing is real-time behavioral targeting. So even when you have staggered pipelines, what you would see is that your user profile gets updated after every n hours. That n could be anything from a couple of minutes to a couple of hours. So you see quantized changes to the user profile, and that is often not good enough. So we came up with another solution known as the real-time behavioral targeting pipeline that helps us achieve millisecond latencies in updating user profile as fast as we see the user event happening. So this is our current offline BD profile pipeline, where we get the data, the requests and the response on ad servers. They're pushed to logs, streamed through our pipelines. We generate the BT profile. They get pushed to Blackbird. So Blackbird is actually our homegrown application layer on top of HBase that has been tuned for amazingly fast lookups. It's very, very scalable. The lookups are of the order of 2 milliseconds. And our ad server basically consults Blackbird, looks up the user profile, looks up other restriction-related activities, and tries to figure out the behavior and what sort of ad it should publish. So now what we do is, as soon as the ad server receives an event, it pushes that event to Blackbird as well. So Blackbird follows an append-only model. So we get that information in real time onto Blackbird. And while it is making a decision next time while bidding, it treats both the profile generated by the batch pipeline as well as the real-time pipeline and merges it and uses it for making a better decision. So this helps us in basically reducing the overall latency. Now, the question that you would ask is that, OK, hey, you have real-time behavioral targeting, then why do you actually need the offline pipeline? Turns out there are certain issues that we need to address that still makes batched updates a much preferred way of doing things. So one of the most important thing is that the batch profile is aggregated over several hours. So remember, we use offline HBase instance in our case for aggregating user data. So we push all the features that we generate, billions, trillions of them, and using the column qualifier schema that we have, we are efficiently able to look over a given specified range of users. So let's say we want 30-day profile of a user, we can easily do that. We want 60 days, we can do that. So that allows us to basically get all the features for a given user, thrash them out, do filtering using the model, do all sorts of clever stuff, and push it to our online store. That is not really possible with real-time profile, because you get an update, you get the update next time. Whenever you get an update, you need to make a decision whether you want to include it or not. You don't have the ability to look in the future. So that is something that batch profile gives us. The next thing is the processing load. So as I said, Blackbird is optimized for ultra-fast lookups. So we need to make sure that, oh, sorry. Yeah, so we need to make sure that we have minimal disk footprint, and we are able to do things pretty quickly on that. The other most important thing around this is that Blackbird sits in our data centers. So all the requests that it gets, all the requests that it is processing for a single specific user is only for the requests that come to that data center. While when we have batch profile, we can efficiently look over all the requests that have been to all of our data centers, and we can have a collective profile that is much more powerful. So those are the things that tell us that, hey, batch updates are still much more useful. So as a firm, we have grown pretty fast over the past year. Deloitte has ranked us amongst the top firm in the top 500 list that they publish about the fastest growing firms in telecommunications, technology, clean energy, and things like that. For us in the data team, it means that we have a lot more data to process. Specifically, we have seen like more than 3x growth in the number of events that we store and process. We are entering into mobile, so we have a lot of mobile app interactions. We have a lot of geolocation data. So we ran into many scaling issues around it, and we'll discuss a couple of case studies that probably would be useful for you guys as well. So the first one is HBase region hotspotting. So as Chandra mentioned, we use HBase to store our features. And since we have a lot of events to process, specifically more than 50 billion of them, and we extract a wide variety of features from them, so we run into trillions of features. And if your HBase row key design, schema design is not perfect, then you would definitely run into this issue of hotspotting. So basically what hotspotting means is that one single region in HBase faces high write load, and that causes it to split. So now when the region splits, it causes the region server to use high CPU. And since we have other jobs running, other jobs on Hadoop that have nothing to do with HBase, those jobs suffer, and we see like tasks failing, task tracker getting blacklisted, so our cluster performance degrades. And that's a pretty bad thing, and our ops guys are definitely not OK with that. So this is what happens. Like even after hotspotting, there might be a case where the new HBase region that you created, it might still have issues. So one of the easiest way around that is to solve your row keys. So internally at Rocket Fuel, what we do is that we have a fixed length hash prefix, which is based on murmur hash. So we extract the top 4 bytes out of it, and we prefix it. What this allows us now is that we can create our HBase table when it was created at the first time with uniform pre-splits, so that now we know that each of the HBase region contains similar amount of data. And what it helps us in turn is achieving good latencies while reading the data. So our read pattern is that we identify users that we deem are important for us, and then for those users, we read a set of data which corresponds to a certain amount of days in their profile from the HBase instance that we have. So a good way of reading this, since you know that each of the region that you have contains similar amount of data, is that let's say you have an input file containing all the user IDs, and it's in K-splits. So you can push it through a key partitioner that actually converts it into M splits, where M is also the number of regions that you have. And the boundaries of those splits corresponds to the region boundaries. So now when you run a MapReduce job using this split file, using this map split as your input, you would be actually talking to just one single region, and that would mean that your reads are actually optimized quite a lot. So just to put things in one go, so our key partitioner, basically, it reads region boundaries of the HBase table. It sorts and sorts the row key accordingly. So this sorting and sorting happens in the reduce phase. So one thing that you could definitely do, and we do, is that we use multiple output formats so that we don't end up using too many reducers, because in this case, in the absence of multiple output format, you would end up using as many reducers as you have the regions. So that's one thing that you can do, and that definitely reduces our read latencies over here. Now, the next thing that we went into was the network bandwidth trouble. So we have been growing pretty aggressively. We have 8 data centers now, a couple of them on the West Coast, a couple of them on the East Coast. We have data centers in Europe, in Asia. And we have been processing a huge amount of data. So that means that at some point of times, we overshoot the bandwidth limitations that are available to us. So those spikes that you see over there are data volumes that overshot the bandwidth that we have. You could also see the sinusoidal curve of traffic, and that perfectly fits in with how people browse during the day. So you have higher activity during the day and lower activity during the night. But whenever we shot the bandwidth limitations that we had on the pipe, we faced all sorts of delays. So any data that goes on the wire, it faced delays, be it Redis, MySQL, Blackbird. We were unable to consult our campaign metadata, our budget managers effectively. And that meant that our bidding, our core business was hampered. So we had to actively look into solutions around that. So we came up with a 3-pronged approach. So one of them was to use protobufs everywhere so that we avoid any extra overhead, so that we minimize any overhead on the wire. The next one was to throttle the writes that we were doing, so basically delay all the RPC creations that were happening. And the third thing was geo-splitting. So as I alluded to our Blackbird instance earlier, so it comes with a very nice analytics framework that allows us to analyze how the user profiles are being accessed, what is the access pattern, and so on and so forth. And what we found was that there was some user profile, actually quite a few user profiles that we were pushing to certain data centers that were not being accessed at all. So that actually means that, for example, we pushed a profile for a user to China, let's say, and the user didn't show up in China. There was no request for that user coming up in that data center. So that meant that we were actually loading that data, moving data around that was of no use. And since we are in the optimization business, we sought to optimize that problem. So we came up with an algorithm, we came up with a workflow that periodically generates some geo-split rules. Essentially what that is that it consults a user's visit history, where all the user has been, what is his profile, and then it looks at the clustered profile of the users, looks at the general migration patterns that we are seeing all across our network, and tries to predict where all the user is going to end up next time for, like, say, next week or things like that. So we came up with a workflow. Essentially, what the workflow does is that it periodically clusters the users, analyzes migration patterns. It's a simple optimization problem that you have, and what it ensures is that we are able to just write those users to those data centers that we have a high confidence that they would be read over there. So we sought to provide maximal coverage while minimizing the amount of data that flows through it. And that format directly fits into our pipeline. So we have a parallel workflow that periodically generates the split rules, and as we are uploading to data centers, we do all sorts of filtering on that. So we are a lean and mean firm, so the mantra that we have is spot a failure and fix it early. And as I said earlier, behavioral targeting is very sensitive to latency. If you have any failures, you're running into failures, your pipeline is delayed, then your campaigns take a very significant performance hit. So that means that you have to proactively monitor the situation. So we have a lot of internal monitoring tools. We publish a lot of logs to OpenTSDB, and we do lots of pattern analysis on that to predict when we are moving out of, let's say, 200-day moving averages, the table sizes are moving out, or the latencies are moving out. And then we can alert. So they are proactive alerts rather than reactive alerts. So as I mentioned, so we have actionable alerts to cut down on the noise. And since we have broken down the pipeline already into smaller chunks, so that means that even if something fails, we are able to recover fast because it was really processing a smaller amount of data. That also means that whenever we push in any sweeping changes, we are able to catch any failures that might happen pretty quickly and recover out of it. And catching things is easy. The main concern is how do you recover out of it. So one of the things that we definitely do over at Rocket Fuel is that we materialize the data at each and every stage as frequently as possible, and we try to keep it with a very short retention policy. So now when the next stage fails, we are able to use that data, and since it has a very short retention policy, we don't run into storage issues. And we have certain scripts that at the end of the day, they sweep through our system and look at all the holes that are there and plug them if they are needed. So that was mostly about this. So we'd definitely like to give our shout outs to the amazing tech community out there, Hadoop, HBase, Hive, Uzi, that we use for workflow orchestration. And hey, we are hiring as everybody. So we were founded in 2008. We are roughly over 700 employees. Right now, we have around 100 people in our engineering team. As I said, we were ranked first by Deloitte in their top 500 fastest growing firms. We were ranked as the 4th most promising firm in America by Forbes. We have more than 1,200 active clients who have successfully transitioned from advertising that learns to advertising that runs to advertising that learns. And yeah, we are open to questions. We have a booth out here. If you are interested in Blackbird, we presented that in HBase Con recently. We have engineers that worked on that team, so if you have any questions, we would be happy to take them. Yeah.
Hello?
Yeah.
So you guys spoke about feature generation, like dominantly, but what about model training? Like how often do you update your models, or do you require a distributed architecture to train models and stuff like that?
The models, sorry, the models themselves are refreshed fairly often. So you can think of it as like, let's say the whole model refresh pipeline takes a few hours. The pipeline kicks in every few hours, starts labeling, training, backtesting, calibrating, and so on.
Okay.
So yeah, I can't say exactly how often, but it's safe to say that they are trained often.
And that retraining is like it's done automatically?
Yes,
Okay.
the retraining is all completely
Like a
automatic.
continuous deployment kind of.
And yeah, it's only that if there is some new model that we want to consider, only then there is some manual effort. Otherwise, they just continuously retrain, refine, and get better as time goes on.
And is the training done on a distributed architecture or?
The data preparation is fairly distributed. We use Hadoop, we use Hive, and everything like that. The training itself, it depends. Some of the training happens on like large single boxes. Some of them happen on a distributed, depending on the use case we see. But we have fairly large boxes that many models can be trained on a single large box as well.
Okay. Thanks.
Mm-hmm.
So when you train a model, how do you determine how far back you want to trace the data? Like in your system, you may have data of 10 years ago, but not data older than 1 year may not be accurate for a model. So how do you determine the optimal length for the historical data?
So that basically depends on the type of model that we have under consideration. We have a fairly big modeling team that does all sorts of research into this. So I guess this is more of a research topic, and there's not one answer that fits all of the models.
Okay.
So for example, a behavior-oriented model might have different criteria compared to some other model, right? Something that's optimizing for just pure clicks that might have a different training period compared to a behavior-oriented model.
Okay. So, I mean, do you have some way to automatically determine this kind of a time period, or is it something determined manually by your data scientist team?
I guess this is determined, you can say, with a little bit of intuition, with some data science as well. And they normally start small, test it out on something, and then we have infrastructure that allows them to try it out on a much larger scale until we are satisfied that, yes, this is like a production-worthy model, at which point we kind of start running it on a regular basis, you can say.
Okay, thank you.
So after you decide what ad to serve, so it goes to the exchanges, how do they decide that which one of them they should pick?
So basically what happens is that whenever a bid request comes, it doesn't come to us, it comes to other partners that they have as well. So when we respond, other people also respond to that ad request, and there's an internal auction that the ad exchange does, and then we pay the second prize on that if we win.
But how much information are you giving them? Because they have to also run an algorithm to figure it out.
So we give them a link to the creative that we want to show and how much money we are willing to pay.
I think they have to run fairly minimal, you can say. It's pretty much like, does the ad kind of conform to their exchange restrictions or norms or whatever you want to call it? Is this like, safe ad? And how much are you willing to pay for this opportunity? And then they just run that auction. So at that point, I don't think there are any fancy algorithms there.
So when the request comes to you from the exchange, what kind of information they are giving you? Do they give you like a mobile location, some sort of IDs? What is the information they pass?
Depending on the exchange, you can imagine, at a minimum, we'll know things like what website is this user in, some of them also provide you the category. Is this like a news or a sports website?
Mm-hmm.
And definitely some of them will provide location as well. If it's like a mobile exchange, there's a better chance of that. So it's not like all of them provide the same thing. So it's like, but at a minimum, most of them provide this kind of information.
Yeah.
So we can certainly, use that.
For the machine learning algorithm part, right? Do you use some like a BAS or some like a proprietary other algorithm?
Yeah, the algorithms are fairly standard. It's like logistic regression, naive Bayes, and so on. And usually, the way we think of it is that a lot of work goes in the data preparation and labeling and everything. And then after that, the training steps themselves, we rely on quite a few standard ones as well. and some that have been written in a custom manner. But yeah, it's essentially the scale of the data that it trains on. That's what usually provides a better predictive power.
So because for the ads, usually you have like a performance-based and some non-performance-based, right? For your algorithms, do you distinguish them, like in different categories?
Yes, so maybe I can explain it this way, right? There are some ad campaigns might have a goal that, let's say, it's not like whether you're clicking on the ad or not, but whether you're actually going all the way and either making a purchase or signing up or doing some actual action, right? So for those kind of interactions, we might have a separate model, while there might be a different model that's purely predicting whether, is the user going to click on it or not, if that's what the advertiser cares about. So yes, depending on the goals, there could be different models, or sometimes we could use the same one as well.
Okay, so thanks. My last question is that it's the discussion so far looks very like a display, I mean on the desktop, right? So do you guys also cover like a mobile?
Yes, mobile, video, social, all of them. Yeah.
So this ads impression is sent to both like a desktop and the mobile devices.
Right, depending on whether the request comes in from a mobile device or a desktop, yes, we would be able to serve on both.
But for me, it sounds it's very different. These two, display ads and the mobile ads, they're very different. Can you address
you're right in the sense that one of the things we are also looking at is like, let's say, mobile-specific models, right? Models that might better predict a relevant ad on a mobile display rather than on a desktop one. So they are a little bit different, but there are a lot of common challenges as well.
Okay, thanks.
Okay, my question is related to the processing path. Like when the request comes in and when you give the response back, can you share what are the different steps it goes through and how much processing time you spend in different stages of that? And or what is the bottleneck?
I can provide a very high-level view, right? Essentially, since this is a real-time interaction, we have to pretty much respond in milliseconds, right? Of the order of, let's say, like 100 milliseconds, right? Let's say. And within that time, it's essentially like what we showed, right? I mean, you extract a certain set of features, that are coming from the bid request. We have a certain set of eligible ads, and essentially figuring out, assigning that scorecard, saying that, for this ad, it's more relevant because it's scored higher based on the weightages compared to another ad, and so on. So I don't know if there's a specific bottleneck that I can allude to there, but this is where the bulk of the time goes in.
So maybe another way of asking is, let's say today it is 100 millisecond. You want to break it to 50 millisecond, let's say for particular ad or campaign. Where would you target? You will scale out, or you will have the higher frequency CPU? Is it CPU bound or memory bound? Or
this particular step, you can say, is a little more CPU bound, right? It's like pretty much like you can cache many things in memory about the ads and so on, and then it's literally a question of scoring each one. And so yeah, so that's where we would put our efforts.
Okay, thank you.
Oh.
Thanks for your presentation. I have a question regarding the comment that you mentioned, as the delay increases, the effectiveness of the models goes down. That's intuitively clear. But can you quantify this? For example, if the delay increases from 1 hour to 1 day, how much effectiveness is going to go down? I mean, the number is somehow, if you can quantify it.
So we run simulations internally on some test campaigns to calculate what kind of lift we are observing when we follow different kind of pedagogies over here. So I'm not sure if we would be able to give you specific numbers around that, but we have been seeing incremental lift on that. So it's definitely well worth the effort to seek out the real-time behavioral targeting pipeline for that.